Thank you. Hello, dear colleagues. I want to present to you my topics. It's about biopolymers because nowadays we use our polymers in all parts of our lives. So we get a big problem with some ecology elements that a lot of our polymers it's not normally used. So our department proposed to change some kinds of classical polymers for biopolymers, and a lot of polymers use it in electronical ways. So our topic is about a development of biocomposites based of polyhydroxybutyrate natural and polyhydroxybutyrate attractive with graphene fillers of some piezo-resistive elements. Our Center of Polymers and Carbon Materials, we produce some kinds of modification of different fillers. For example, the first step of our work is eco-sensor. What does mean? It's a sensor with classical properties, use it in electrical ways, but in the same time, it consists of biopolymer matrix and some kinds of fillers, for example, graphene nanotubes or some GNP or TNT. So the first step is how it looks to preparing our materials, because it's materials measurements in our way. The first step of that, we use it natural polyhydroxybutyrate powder. Then this is materials is so crystallinity, it's of high crystallinity, it's not possible to use in flexible films, for example, what we get in the end of our measurements. So our colleagues proposed to lower the molecular highest of the crystallinity to get some kind of flexible material. So we made some modification of this and get attractive polyhydroxybutyrate. It's more flexible materials. The matrix a little bit different with highest molecular mass of some elements of the materials. The next is graphene materials. We use the GNP, TNT, and make some functionalization of graphene oxide. So we use some kinds of different materials in our films, and we get graphene with polyhydroxybutyrate composite. It fills for our materials for our sensor. You can see the procedure, how it looks like in our methods. We start to preparing a normal classical solution casting with using electrosonic disperse for the nanotubes, and we get the end of this process our films. What kind of fillers we used? We used graphene, it's the GNP, TNT, and TOX. What we use it after the functionalization, we change some concentration of these materials and get some proportion of GNP and TNT and GNP and TNT-OX. So our functionalization of TNT to get TNT-OX, it looks like oxidation of humus methods. We get it in our laboratory for the synthesis process. And here you can see some results of our measurements. It's some imaging from the polyhydroxybutyrate natural with polyhydroxybutyrate attractive. The first picture, you can see how it looks, the blend of two kinds of polymers, one of them of higher crystallinity and with lower crystallinity. And in the right part of this picture, you can see how it looks like with some fillers. For example, it's 2% of the mass. So you can see how it agglomerate looks inside of the polymer matrix, how it change. You know that when we put some graphene materials inside of our polymer matrix, we get more crystallinity structure. So that's why we need to use polyhydroxy butyrate attactive, because for the get flexible films in the end. More better to see it's our IFM 3D imaging to see the fracture surface of pure polyhydroxybutyrate in the left side of the picture. So how it looks like a films without graphene fillers. And in the right part, you can see how it looks like use it some center 2% of mass. It's a little bit similar for other concentration of materials. That's why I just show how it looks like with filler and without fillers, because in other kinds of fillers, for example, GNP, some blends with GNP and TNT, it looks like similar surface for the second pictures you can see here. And the next step is a characterization of a DMA, because we need to see how its structure change with our different fillers. So in this pictures, you can see how it in these lines change the temperature of the gay to the DMA analysis, because with a normal blend of PHB and PHB attractive have a highest temperature, but when we put some kind of fillers, it's a little bit changed. You can see it in this part of pictures, and what is the best of our modulus of loss and factor values of the consist and under. It's a strange modulus, you can see first pictures, and second pictures, it's peaks with loss modulus of the DMA, and it illustrates the temperature of depends of the strange modulus, loss modulus, and loss factors of the delta, and for the polyhydroxybutyrate naturals and some kind of fillers. And on this side, you can see how it changes with different fillers, with different materials of the graphene. What we get in the end of our measurements with these materials, the main things what we need to get is some electrical properties for the piezoresistive characterization. In this picture, you can see that we use not just the different kind of fillers, but we use the different kind of concentration of fillers. We start with GNP, and we see that the optimal concentration of the mass, it's 2%, because in the other steps, it's a little bit change our conductivity properties, and the optimal of our measurements shows that we need to choose of all of these samples. We try from 0.5 to 6% of the mass, but we choose the best things to change the fillers, it's 2%. Our electrical piezoresistive characterization show us how it get as different kind of fillers. For example, in the first picture, you can see it's fillers TNT. Second one is GNP. The next one is 2% of TNT-OX, and blend TNT-OX and GNP. So in the end of our measurements, at the end of our research, we check that the best position for us for our nanomaterials is use it blending with TNT-OX and GNP with 2% of the mass of both of these materials, and we get the highest peak and normal piezoresistive measurement of the end. And the biopolymer films, they use it in a lot of kinds. Nowadays, it start to use it in a lot of kinds of fields. It looks like package films, and our field looks like electrical to change the normal classical polymers for the biopolymers with biodegradable process. And now we start slowly to go to this film because it's not so quick. It's so expensive to use biopolymers nowadays. Some kinds of graphene fillers show us that we can change it in the future, but step by step, we're going to find some new kinds of materials with not highest price, looks like PHB, and to make a tacti PHB because it's long process, it's the highest of some modification process, but is going for 6 months. It's a long time to preparing these materials. So thank you for your attention, and have you any questions?
Thank you, Vicky. Do we have questions from the hall? Probably some questions from internet or from Kiev. Okay, I have a small question, two questions. How is the weather in Zabrze?
Good question. Weather is good. It looks like similar with Kiev now because it's similar part of territory.
Because in Yaremchuk we have very good weather now. And the question about your presentation, you showed that you put the optimal weight percent of carbon nanotubes in composites is 2%. And
Yes.
do you, when you form the composites, it is structured or it was formed by extrusion? What is the process of formation?
We propose the series of our samples, for example, from 0.5% to 6%, and check some electrical properties with these films. And then we check that conductivity is better with 2% of our materials, of our fillers. Then we make the same process with 2% of different kinds of fillers. It looks like blending with GNP and LX 2% or GNP 2%, and then we choose how it changes with temperature because it's not consist of the normal electrical properties, but it's changed with temperature. And these polymers, it's a specific polymers because it degrade in some kinds of temperature. For example, highest more than 180 degree, it start to more higher of degradation, and then it's not possible to use this polymers in some kinds of field. So we need to choose fillers, to choose some materials with the same properties, because with higher temperature, it's destroyed of our structure.
Okay, thank you.
Thank you.
So probably any other questions? No? Okay, thank you. And please send best regards to everyone in our laboratory.
Thank you.
Bye-bye. Thank you.
Bye.
And the next speaker is Danhu Zhang. He is our PhD student, and he will make the presentation on analytic mathematical model for multi-layer thickness of high-density polyethylene pipes at thermal part fusion welding. Danhu, are you here?
Yes, I'm here. Yeah.
You are
I'm here now.
So the floor is yours.
Okay, thank you. So, do you watch my screen now?
We hear you. We hear you. So please.
Okay. Thank you. Dear professors and dear friends, my name is Dong Hu. I come from the Department of Plastic Welding in Badung Electrical Welding Institute. Today, the topic of the study is analytical mathematical model for multi-layer thickness of high-density PE pipes at thermal bud fusion welding. This topic includes some following contents. First one is introduction. Second one is research methodology. The third one is results and discussions. And the last one is conclusions. Now let's start from the part one, introduction. Background. High-density PE pipes have made significant contributions to our daily lives. Thermal bud fusion welding technology is the preferred method for connecting large-sized high-density PE pipes. And the formation of the high-quality welded joints usually depends on the proper melting layer thickness affected by welding parameters. Numerous researchers have studied the characteristics and mechanisms of the melting layer thickness in high-density PE pipes. However, a limited research has focused on the theoretical analysis of how the melting layer thickness of high-density PE pipes changes over heading time during thermal bud fusion welding. The purpose of study is to develop a reliable analytical mathematical model for predicting changes in the melting layer thickness as the heating time progress at a fixed heating temperature. Based on this model, in the future, the optimal welding parameters for the high-quality welded joints can be found out for different large-size, high-density PE pipes, resulting in avoiding experimental budget and saving computational cost. The study also provided theoretical foundation for high-speed welding of polymer in the future. There are some objectives about the study. First one, developing analytical mathematical. And the second one is developing a two-dimensional numerical model in access fluent to obtain the multi-layer thickness with the specific dimensions, like outer diameter is 200 millimeters, SDR is 17, and the length is 15 millimeters, and the seam non-linear thermophysicals properties. And the last one is compare the results from the analytical mathematical model with those from the numerical model to verify their consistency and reliability. Now, part two is about research methodology. In the study, we used nonlinear thermophysical properties is benchmarked based on existing literatures, and then the initial temperature was set to be 28 degree, and the heating temperature was set to be 240 degree. The table one is about thermophysical properties of high-density PE pipes in response to temperature change, and the table two is about the thermophysical properties in solid phase and melted phase. And now let me introduce about the mathematical model in the study. An analytical mathematical model was developed using the following some equations. The first one is about energy governing equations. The second one is energy conservation equation. And the third one is about boundary conditions. And the last one is about error functions. So there is about scheme about how to the heat transfer from the end of heated to another end. And about mathematical model in the study, we only considered a one-dimensional model. There are some about equations about mathematical. The first one is about energy governing equations. There is two equation. There is two energy governing equations about in a melting phase and in the solid phase and the energy, and then the energy conversation equations is about is is about this one, yes. And the boundary condition, uh, uh, there are four boundary conditions. The first one is about when there is no heating time, so each time is zero. So the temperature of the high density PE pipes is the initial temperature, so it's T0. And this one is about when we start when we start heat the this end. But now its location is at this surface. So now it's the temperature equal to heating temperature. And this one is about uh, another end. It's a like end. So this temperature is equal to the initial temperature is T0. Yeah. What's the most important in about boundary conditions is this one. And this one uh, involves about temperature continuity. And the next one is about error function. This one uh, is used to describe about the relationship between the distance and heating time. So we use these four equations, and the last we can get about mathematical model function is like this. It demonstrates like exponential functions. For simplifying the complexity of developing analytical mathematical model, some assumptions were taken in the study. One, we just considered one-dimensional heat conduction. Second one, we neglected the effects of convective heat transfer between ambient environment and the surface of high-density PE pipes. The third one is neglecting the effects of heat conversion in melting region. The last one is about density at phase change interface here is equal to the average solid and melting density. So now let me introduce about the numerical model for confirming the reliability of the results. from mathematical model. That's in the study. The numerical model was also developed using ANSYS. In ANSYS model, I considered the effects of heat convection between air in the environment and the surface of high-density PE pipes. So there is some words about the uh, numerical model. Because I want to get some results with hidden time progress. So I choose the transient safety and consider its gravity into consideration. Because there is no big flow or there is no velocity. So we just I just take a laminar model or take into consideration. Because I need to get accuracy results from the melting region. So in this case, sorry. So in this case, I make it anti-smash and another part is a cross mesh. In this model, the elements of mesh size was 0.2 millimeters with 15,000 and 60 nodes and 29,500 elements. In this numerical model, the heating time was set 180 seconds. And thus the number of time steps was set to be 360, and the time step size was set to be 0.5 seconds, and the maximal iterations was set to be 30. The computational cost of high-density PE pipes in this study was about 10 minutes. The part three, some results and discussions come out. So there are two pictures about temperature distribution and the mass liquid fraction. So as we can see, from the temperature distribution, the temperature distribution exhibits water array pattern from the upright and to the lower left, like this. Yes, that is a pattern. And about the mass liquid fraction, like the solidus and the liquidus line at mass fraction was distributed in an arc shape, point to the non-heated end of high density PE pipes. It's like this. So let's one. So I make some comparison in mathematical and numerical. Both the mathematical and the numerical models demonstrated an exponential relationship between the melting layer thickness and the heating time. So like this, its curve demonstrates an exponential relationship. From here we can see something. Blue curve denotes analytical mathematical model results, and red curve denotes about the numerical model results. So from this picture, we can see results from numerical model were consistently lower than those of the mathematical model. That's why, because in numerical model, I considered the heat conversion between Abin's environment and the surface of high density P pipes. But in my mathematical model, there is no considering such likeness. By comparing the melting layer thickness from the analytical mathematical model to the numerical model, it was found that the difference between them was within 18%. Yeah. So there is about some results from modified mathematical model because a previous model maybe let some mistake. So now I make it furthermore about mathematical model. So now there is some results. Uh, for this one is about simulation. Yes, as you can see, there is a melting layer thickness is about 4 millimeters, 4 millimeters. And from this picture is from MATLAB. The results is same as ANSYS results. Is that here? Is also about uh, 4 millimeters. The yesterday before I carried out experiment about this study. So that is I calculated thickness of melting rule. It's approximately close to 4 millimeters. Based on these three results, you can verify the results from mathematical model. Maybe it's okay. It's all right. So now the last one. Let me make some closes. The first one is analytical mathematical model and numerical model to predict the metal layer thickness as heating time progresses were developed. And the second one is about results. Its results error remains within 18%. The third one is about in the future, we can take the effects of heat conversion between the ambient environment and the surface of high density pipes into our mathematical model. So about something that's my report. So now that's all. Thanks for your attention.
Thank you, Dunhu. Do we have questions? Yeah, please.
Thank you for your presentation. You told us that your model is one-dimensional.
Yeah,
And,
right.
Yes, is it?
Yeah, right, yes.
Can you show the slide number 18?
18, right?
Not 18,
This one?
16.
16, this one, right, okay.
Previous one.
Sorry, 16.
Yes, and in this figure, we can see that the temperature distribution is really so we can see here that the problem is one-dimensional. So the question is why you used the two-dimensional computational domain in ANSYS?
Because in ANSYS, I will use the two-dimensional. That's why there is some results. First one, using two-dimensional model, it can be reduce the computational cost. And that is can improve the increase computational efficiency, right?
You told us about a large amount of nodes and so on. I think you can decrease this amount using the one-dimensional computational domain.
You mean that in our mathematical model uses one-dimensional model, but in our simulation model you use two-dimensional model, right? Okay. How to say?
Yeah. Any other questions? Probably Kiev. Okay. I have short. Yeah. We have a question from the conference hall.
Thank you for your interesting presentation. And please explain, why do you call that the temperature distribution exhibits water ripple pattern? Because temperature distribution is monotonical, as I understand. Maybe it is just an effect of your post-processing procedure. Thank you.
Okay. Sorry. Maybe by some internet. I didn't hear your questions clearly.
Can you please explain one more? Why do you call that why do you tell that the temperature distribution exhibits a ripple pattern? To my mind, the temperature is monotonical inside the computational domain.
You mean
Let me repeat. The question about the gradient of temperature. Why we have such a gradient? Am I right?
Yeah.
We will discuss it later.
Okay. Okay. So in the institute, you may meet and discuss all the questions about that. Okay, thank you. And Danku, I have a question. If I understand right, yesterday, did you confirm the modeling with experiment?
Yeah.
So that's good result. Okay, any other questions? Thank you very much.
Thank you so much. Thank you all. Have a good day. Bye.
Okay, and the next speaker is Anastasia Litvin. She is a student from National Technical University, Kyiv Polytechnical Institute of Igor Sikorsky. And our staff, she will make a presentation about optimization of PET bottle recycling for filament production, a comprehensive study on 3D printing parameters and material properties.
Good afternoon, everybody. Thank you for meeting today. So my research is dedicated to the development of a prototype device for recycling PET plastic bottles into filament for subsequent use in 3D printing. And this approach not only reduces the amount of plastic waste entering the environment, but also conserves resources and energy required for the production of new plastic and resulting in significant cost savings. And additionally, PET filament exhibits shape memory effects, making a potential candidate for application in 4D printing technologies. So this study examines the design of a device for recycling PET bottles into filament, the process of manufacturing and testing the device prototype, the development of recommendation for optimization the PET bottle recycling process into filament, and the research and comparison of mechanical, thermomechanical, and colorimetristic properties of PET plastic before and after recycling into filament. So I would like to tell a little bit more about constructions details. All plastic assembly parts and components were 3D printed from PLA filament based on CAD files. So on the picture number 1, we can see supports that are attached to a wooden panel, and the front and rear parts, it's number 1. Oh, sorry, it's number 3 here, of the filament winding drum are bolted together. They are driven by DC motor, and gears are used to rotate the drum, as we can see on the right bottom picture. A bracket also screwed onto the surface holds a heater, it's number 2, equipped with a thermocouple and a nozzle through which the PET strip and finished filament pass. And a temperature controller is number 4 is mounted on the surface. The front section of the setup features holders for buttons and controls the strip width. It's number 5 here, which depends on the bottle height adjuster, as well as power switcher. It's number 6. The cutting assembly number 7, as well as pictures 1 on the top left side, includes a rod to secure the bottle, and cutting is achieved with sharpened bearings positioned with their cutting each facing each other. So it's how the bottle is cutting. And additionally, here is the formula because we need to know the width for cutting to ensure it passes smoothly through the extruder before being converted into filament. So since the volume remains the same before and after the PET is converted, this allows to use the following equations that we can see on the first picture, where D is the diameter of filament and A is thickness of filament. So to prepare the bottle for extrusion, we need to remove label, cleaner adhesive, spots, and we need to insert valve into the bottle cap to which an air pump is connected. And in our case, we made a hole in the bottle cap and inserted a fitting with a hose attached to it. And the bottle is inflated with air to pressure above 1 bar. A heat gun is used to heat this bottle because it's smoothing the surface. After that, we made a small cut, approximately 10 centimeters long, and fed through sharpened bearings acting as cutters. And after that, bottle rotating around the axis, and cutter converts the bottle, the strip into filament. The strip is heated in this like it's passed through the nozzle and forms the filament. Like I can show this video, so it's more detailed, explained how the system works. So it's moved by DC motor. Here is filament. We can see 230 degrees in thermocontroller, and strip pass through the nozzle, forming ready filament. Yes, so it's have this system functioning. Here just small slide to represent some internal processes, and it shows electrical connection schematic, and we also made universal fitting for the compressor hose, and it was modeled for bottle inflation and then machined in the lab. Okay, so also I reviewed some of problems that can arise, and they arise totally when I printed the details for the device from PLA. So I considered next parameters, and by the way, I used Gambit 3D print Gamma. So because parameters are varied from the printer you use. It's very important to consider print speed, temperature, infill density, layer thickness, and surface type to ensure the sufficient adhesion. Because inappropriate parameters can result part exhibited poor surface quality with deformed filament layers that had weak adhesion with each other, causing a curling defect or other defects. And high layer thickness and infill density cause the material to become more prone to deformation due to increased internal stresses during cooling. So the issue of non-sufficient bed adhesion for the printer's bottom rates can impact the quality and integrity of printed parts between each other when adhesion of the surface is inadequate. The tangential component of the extruder speed can really detach the part from the print bed, and it's leading to deformation due to the delamination of the lower layers from the platform surface. So our solution was to use non-stick coating. It was painter's tape. We put it on the surface of beds, and it really showed significantly better adhesion to PLAs and other materials as a paper. So to resolve any problems that can occur, it's better to always reduce layer thickness, because thinner layers can improve adhesion and reduce deformation. And adjust infill density because it reduces internal stress. Better optimized print speed. You need to consider that slower print speed helps avoid material overheating, because each of layer has more time to cool down. And adjust the heating temperature, also very helpful, because high temperature can cause material melting. Correct platform surface helps to avoid deformation and the delamination of the bottom layers from the print platform. So the next steps in my research was testing results for mechanical characteristic for both bottle with raw plastic and filament after extrusion, and comparison of their properties. So we can compare parameters such as stress and strain at breaking points and yield points, because this allows to analyze the material endurance and resistance to physical loads in the future. So experiment test on its Shimadzu AGS X10 kilonewton tensile machine, and I conducted 3 experiments on the PET tape and 3 on the filament. So if we analyze the curve on these graphs, the part of curve that can be described per linear equation, so we need to isolate this part, and then we can use the following equation for finding Yungus models for both raw plastic and filament. For this part that is described with linear equation, and also the graph for filament on the right hand side, we can see the different structurally from this obtained for PET tape, because we can see for raw PET, necklink was observed along the entire length, and we can see on the graph how it's formatting the neck, but in the curves for the filament, there are smoother transitions from elastic to plastic deformation, and there is no like very visible peaks indicate necklink formation. So it's depending on the strengths of atomic bonds. The crystalline structure influence how far this bond can stretch, and therefore it can be asserted that after heating to melting temperature, what we did for filament, molecules reorganize, and it's leading to intermolecular strengthening, making the filament probably more resistant to deformation compared to the raw PET. So here's the results comparison. So for filament transitions to a plastic deformation state at a lower strain values and lower pressure, which is logical since thermomechanical analysis during reheating PET demonstrates that within the temperature range from room I'll show it later in the next experiment. So from the temperature range from room temperature to the melting point, internal stresses are released, and it makes the filament easier to break compared to raw PET, which our results demonstrate. And breaking occurs within, if we look at breaking points values, breakage occurs within stress values on approximately 165 to 185 megapascal for both the filament and PET tape. But as we can see, the strain values for filament breakpoints are lower. Possibly it's due to grain growth during recrystallization, which makes the material more brittle, but to prove it, there needs to be conducted more researches. Next analysis was thermomechanical analysis, and in the graph on the left, which shows PET before processing, the stress in the sample begins to increase at 103, approximately 103 Celsius degrees due to residual plastic stresses within the material, as PET has shape memory. So at 103.80 degrees, the curve levels out. It's indicating that the thermal expansion of the sample is balanced by the applied load, meaning the sample is in equilibrium until around 240 degrees. To be more query, it's 245 degrees, and its determinant is melting temperature. And it's the point where indenter fully penetrates the sample, signaling complete melting of material. We can see here the glass transitions temperature, and it can be determined as an intersection of the linear portion of the graph with the sample's expansion and the tangent curve after the onset of expansion. And temperature of glass transaction is 108 degrees. And it's which falls within the values obtained from the DSC analysis results, and it corresponds to the value from another experiments I found when I did my research. So we can see that from the range of 20 to 99 degrees, the sample expansion as function of temperature is approximately linear. Thus, the coefficients of thermal expansion for unprocessed pan can be determined by using formula you can see on the screen. And also, I conducted second experiment, and as shown on the graph on the right, there are two steps of the experiment because it helps us to allow relaxation of residual stresses. So the sample is firstly heated to 210 degrees. And by this point is then cooled to room temperature and reheated to the melting point. So in this graph, the red curve represents the initial heating for stress relaxation. It's the purpose why we're doing that. And the gray curve represents the second heating following the heat and cooling cycle. The coefficients for thermal expansion obtained through this method vary as the material with internal stress, like shown on left graph, tends to exhibit a lower coefficient of thermal expansion. Of course, this is because some of the energy applied during heating is used to overcome these stresses, and once these internal stresses, once they're relieved, restrictions on atomic movement in the crystalline lattice are removed, and it allows the material to expand more freely in response to temperature changes. So this method can effectively describe the thermomechanical characteristics of part printed from filament as PET go through same stages during filament production. So it's heating, so here we can see the results for glass, for glass transition temperature, melting temperature, coefficient of thermal expansion up to glass transition temperature, and after glass transition temperature. We can see that the coefficient of thermal expansion after glass transition temperature is extremely higher than up to glass transition temperature because we released internal stresses and relaxate this residual stresses as I described before. The melting temperature in approximately the same range, and we can see the glass transition temperature is also approximately in the same range, but because we use a different word, it can vary. So the last experiment, just to confirm the data we received in previous experiment, are obtained from differential scanning calorimetry analysis using the DSK-Q 2000 apparatus. 2 runs were conducted for both PET and filament samples to eliminate internal stress, as we performed before, in order to remove the material's history. So in the first run, I do not have here the graphs for the first run because we cannot take a lot of information from there. So the sample was heated to its melting point, cooled down, and the process was cycled repeat for the second run. For DSC analysis, the PET plastic sample weighing 14 and 9 milligrams was used in the first run. For raw PET, the glass transition temperatures was recorded as 98 and 12 degrees. Melting temperatures recorded as 252 and 81 degrees. And in the second run, which we see in left graph, for ref PET, what is equal to extrusion process temperature, glass transition temperature was recorded as 82.72, and melting temperatures around 247 degrees, indicated that the values remained relatively unchanged after the removal of internal stress. So using the equation for defining the degree of crystallinity, it was obtained that crystallinity degree for PET plastic approximately the same as for PET filament that we obtained on the second run, and the melting temperature obtained for the DSC analysis for PET filament during the first run was 252, and other parameters from the first run graph could not be determined, as I mentioned before, so it's not very informative. Comparative values for the first run of PET tape and filament based on DSC analysis and TMA analysis for PET tape are presented in the table on the top, and is the secondary in the bottom. We can see the value for melting temperature remained largely unchanged after the removal of internal stress, and the results correspond closely with theoretical data. Cold crystallization occurs within the temperature range of 151 for second run for PET to 104 degrees, while the melting process beginning at 226, and the melting temperature values for the first and second runs exhibit minimal differences. So the DSC thermogram obtained for the second one of the filament showed tendencies and temperature similar to thermogram of double extruded PET obtained in another study. So that means there are no big difference between data. So we can when reheating to filament occurs, material does not change its properties during heating run, so we can reheat it multiple times. And the melting temperature for PET plastic determined by both analysis methods also show only minor difference within tenths of a degree. The glass transaction temperature obtained from DSC method for both filamented PET cannot be considered equivalent, whereas the glass transaction determined by TMA methods lower, and this discrepancy may be attributed to difference in experimental methodologies, as during the first run in DSC, the material reaches melting temperature before cooling, but when we use TMA, as I mentioned, I'm melting it to temperature by 210 degrees. So because it's impossible to heat it by to melting temperature because it's can intern the sample and we'll just fail our experiment. So conclusions, here represents the device that has been proposed and allows for the recycling of PET bottles into filament for 3D printing. I showed the process of preparing bottles for recycling. I learned their mechanical, colorimetric, and thermomechanical characteristics for both PET material in raw state and filament after extrusion, and provided with some recommendation for optimizing the process of recycling PET and filament, and included this part in my research. Thank you for everybody for your attention. That's it.
Thank you very much, Nastya, for such presentation. I'm pleasantly surprised. Do we have questions to the presenter? Probably in Kiev. Okay, so what I have to say is that Nastya, being a student, has already got the first commercial project, small, but anyway. And what I can say, we are looking forward to seeing you in our PhD school.
Thank you so much for your attention.
Thank you. And the last speaker for our section is Ilya Sitnik. He's also a student of Kyiv Polytechnical Institute, and in parallel, he's staff of plastic welding department of our institute. Ilya, do you hear us?
Yes, I can hear you. I will show you my presentation in a minute.
Okay, so the floor is yours.
Thank you very much. I believe you can see my presentation and you can hear me well. So I will start. Yes. Today I want to present to you, my dear colleagues, the work we have been conducting as a part of a project of National Research Foundation of Ukraine, was themed as hydrogel materials based on polyvinyl alcohol and silver nanoparticles, cross-linked by electron beam irradiation. So, the hydrogels, what are they? They are gelatinous materials that are primarily used in the biomedical field. The most common applications are bandages for wound treatment, drug and cell cultures delivery, 3D printing and tissue engineering, and self-healing gels. As for the wound treatment, hydrogel provides moisture for the wound bed, therefore helps with regeneration of living tissues. Typical hydrogel is comprised of water-soluble polymers, such as polyvinyl alcohol and polyethylene glycol, polysaccharides, such as polyglutamic acid and pectin, glycosaminoglycans, such as hyaluronic acid, can be added for improved healing properties of acquired hydrogels, as well as for potential biodegradability. Currently, polyvinyl alcohol is one of the most suitable and widespread synthetic polymers for creating gels. It is characterized by high compatibility with synthetic and natural polymers, solubility in water, non-carcinogenicity, and biocompatibility. After dissolving the polymers, they form a uniform solution, which has the consistency similar of that of like sugar syrup. In order for hydrogel materials to be used as bandages, they need to be cross-linked. The most common methods of cross-linking polymer gels are cyclic freezing and thawing of materials, use of cross-linking agents, chemical agents such as boric acid, epichlorohydrin, glyceraldehyde, and electron beam irradiation. In case of electron beam irradiation of hydrogel material, accelerated electrons are almost completely absorbed by water, which constitutes around 85% of its mass. Of the three main reactive forms that are produced in water during irradiation, which are hydrated electrons, hydroxyl radicals, and hydrogen atoms, hydroxyl radicals have the greatest impact of transferring reactivity from water to polymer chains. They detach hydrogen atoms from macromolecules, resulting in formation of macroradicals. That is, hydroxyl group, OH, can capture a hydrogen atom from the polymer bond, forming a water molecule. The radicals created through this mechanism form bonds with other parts of the same polymer macromolecule or with other micromolecules. Part of the hydrogen bonds formed in the process of radiolysis of water combine into hydrogen molecules, forming gas bubbles ranging from 0.2 millimeters to 2 millimeters in size in a sample's volume. Their size and concentration correlate with radiation dose. In the context of use of hydrogel for medical purposes, radiation has an effect on ease of use, which is mechanical properties, and functional efficiency, which is ability to absorb moisture, or in other words, hydrophilicity. The results of thermomechanical analysis of hydrogel materials indicate that the radiation cross-linked hydrogel retains mechanical properties for up to 100 degrees Celsius, which indicates the presence of a stable covalent bonds that hold the polymer network at high temperatures. The working temperature of free-thawed hydrogel, on the other hand, is between 50 and 74 degrees Celsius, and the temperature is increasing with freezing time. This practically allows radiation cross-linked hydrogels to be subjected to high temperatures, as an example for sterilization processes. Radiation cross-linked hydrogels also show the highest hydrophilicity, absorbing a maximum of 150% of water by weight. Free-thawed hydrogels only show about 100% peak absorption, with absorption reducing with an increasing freezing time. Great permeability of liquid and oxygen are necessary conditions for successful wound healing, but the gels themselves do not have antibacterial properties, which can cause harmful bacteria to grow inside the hydrogel bandage and cause a wound bed to get infected. Silver nanoparticles can be used to enhance the antimicrobial properties of gel polymer materials while using various methods of cross-linking gels, irradiation, cyclic freezing and thawing, or plasma. Although electron irradiation can be used for silver ion reduction as well as cross-linking, it can be rather challenging when increasing the silver nitrate concentration above 0.01% of mass. In the case of an effective silver concentration, it will take a considerably higher dose of irradiation for gel to form crosslinks and obtain their mechanical properties, increasing the cost of hydrogel bandages. As an alternative to electron beam silver ion reduction, ascorbic acid can be used. This allows for the hydrogels to be cross-linked with lower dose, meaning it will have desirable mechanical and bactericidal properties due to higher possible silver concentration and at a lower cost. Intense competition is creating a demand for the development of cost-effective, cross-linked, silver-containing gel materials based on polyvinyl alcohol with antimicrobial and antiviral activity. The peculiarities of the structural organization, bactericidal and antiviral properties of hydrogels with silver nanoparticles reduced with ascorbic acid were also studied in presented work. The following reagents were used to form the samples: polyvinyl alcohol, Brent 1799, polyethylene glycol, Brent PEG 6000, ascorbic acid, and silver nitrate. The addition of polyethylene glycol in a basic solution results in an escalation of the optimal cross-linking dose. However, at low PEG to PVA ratios, the presence of PEG significantly enhances both tensile strength and elongation at break. Polyvinyl alcohol was dissolved in water at a temperature of 95 degrees Celsius, and polyethylene glycol at a temperature of 20 degrees Celsius by stirring for 30 minutes. Next, the PEG solution was added to the PVA solution in a ratio of 1:8 by mass and stirred for 30 minutes at a temperature of 95 degrees Celsius. Silver nitrate was dissolved and added to the PVA PEG mixture at a temperature of 80 degrees Celsius and stirred for 20 minutes. At the next stage, with intensive stirring, a solution of ascorbic acid was added to PVA PEG silver solution in the ratio of ascorbic acid to silver ions equals 2:1. The solution was stirred for 3 hours at 80 degrees Celsius. The gels formed in this way were stored for 4 degrees Celsius for 4 days. The cooled gels were irradiated using linear electron accelerator with an irradiation dose of 33 kilogray. This is for non-filled gel, and 66 kilogray for silver-filled gel. The structures of the composites were studied by method of wide-angle X-ray diffraction and on XRD 7000 diffractometer made by Shimadzu, Japan. The X-ray optical scheme of which was performed by passing the primary beam through the sample using cuprum K alpha radiation with a wavelength of 1.54 angstrom and a graphite monochromator at a temperature of around 20 degrees Celsius. Analysis of the structure of polyvinyl alcohol showed that this polymer is characterized by a semi-crystalline structure. This is confirmed by diffraction maxima at 11.2, 19.5, and 23 and 40.8 degrees, which correspond to crystallographic planes with Miller indices 100, 101, 200, and 201. It was established that the introduction of polyethylene glycol into the PVA composition does not affect the structure of the PVA itself, since there is no change in the angle position and intensities of the diffraction maximum. This is indicated in particular by the almost identical relative level of crystallinity of PVA and its mixture with PEG, calculated according to the provided equation, where Q crystalline is the area of diffraction maxima that characterize the crystalline structure, and Q crystalline and Q amorphous is the area of the entire diffractogram in the range of scattering angles, in which the amorphous crystalline structure is manifested. The evaluation of the level of crystallinity show that PVA and his mixture with PEG have values of X crystalline equal to 46 and 47%. It should be noted that the degree of crystallinity of the PEG itself is approximately 88%. The analysis of wide-angle X-ray diffractograms of the initial PVA PEG sample and irradiation cross-linked PVA PEG samples showed that the cross-linked sample, which was exposed to the irradiation dose of 33 kilogray, has a more clearly manifested diffraction maximum at 23 degrees, which corresponds to crystallographic plane 101. I'm sorry, this is Miller indices. Yes, this is 101. Then it should be noted then when cross-linking the PVA PEG sample with an accelerated electrons, its degree of crystallinity increases from 47% to 53%. During the reduction of silver ions in the PVA PEG polymer matrix with the help of ascorbic acid and cross-linking of the sample by electron irradiation, two diffraction maxima at 38 degrees and 44 degrees appear on its diffractogram, which corresponds to crystallographic planes of face-centered cubic silver lattices, characterized by indices 111 and 200, respectively, and confirm the presence of metallic silver in the polymer system. To study the antimicrobial activity of nanocomposite samples, reference strains of opportunistic pathogens were used as test cultures: gram-positive Staphylococcus aureus and gram-negative Escherichia coli. The antimicrobial activity of nanocomposites was studied by diffusion in agar on the Miller-Hinton nutrient medium. Petri dishes with Miller-Hinton nutrient medium were sealed with 0.1 milliliters of inoculum of test cultures of both microorganisms, Staphylococcus aureus and Escherichia coli microorganisms. Pre-made nanocomposites with silver nanoparticles were cut into discs with a diameter of 10 millimeters and placed on the surface of a nutrient medium seeded with test microorganisms. The cups were incubated from 24 hours to 48 hours at a temperature of 37 degrees Celsius. The indicator of antimicrobial activity was the presence of a clear zone around a nanocomposite disc. The larger the zone around the disc, the higher the inhibitory efficiency. A nanocomposite disc without silver nanoparticles served as a control. Experiments were repeated 3 times. The interpretation of the results was carried out according to the diameter of the growth retardation zones of microorganisms around the discs, according to CLSI recommendations. As a result of studies conducted of the antimicrobial activity of silver-containing nanocomposites, it was established the study's samples demonstrate high antimicrobial activity against the studied test cultures of microorganisms. Thus, after 24 hours of incubation of the samples at 37 degrees Celsius, a clear zone was observed around the discs of investigated silver-containing nanocomposites, which indicates the inhibition of growth of microorganisms. The diameter of growth retardation zones were noted at roughly around 20 millimeters for both Staphylococcus aureus and Escherichia coli. In control samples of PVA PEG, which did not contain silver nanoparticles, active growth of test microorganisms and the absence of zones of growth retardations were observed. The next stage of the work was the study of the virulicidal effect of samples. Virulicidal activity studies used influenza virus type A and herpes simplex virus type 1. In screening studies, when searching for new materials with virulicidal effect or expanding the properties of already existing materials, the minimum value of the decrease in the infection titer infectious titer of the test virus during exposure, which indicates the presence of viralicidal effects, is considered to be 2 logarithms to base 10 of tissue culture infection dose, which is the amount of virus required to kill 50% of cells in culture. The studied nanocomposites demonstrate a decrease in viral titer by less than 2 logarithms to base 10 of TCID for both viruses. Thus, relative to influenza virus type A, composites PVA packed with silver and PVA packed with no silver showed a weak viralicidal effect in the range of 1 logarithm and 1.55 logarithm titer reduction, respectively. Regarding the herpes simplex virus, the PVA pack sample did not show a viralicidal effect. The virus titer was within the control value, while the PVA pack with silver composite reduced the virus after they reduced the virus titer by 1.52 logarithm. To determine cytotoxicity, Verocell's culture obtained from the cell bank of the Institute of Experimental Pathology, Oncology, and Radiobiology, and MDCK cells from the Institute of Epidemiology and Infection Diseases, both in Kiev, Ukraine. The presence of the cytotoxic effect of the studied samples was checked by metabolic test, which evaluates the normal functioning and mitochondrial activity of cells under the influence of one or another factor. In the culture of MDCK cells, samples of PVA packed with silver and with no silver show similar effect and reduce cell viability by no more than 8% compared to the control. When examining the toxic effect of the samples on the Vero cell culture, similar patterns were revealed as on the MDCK culture. That is, samples with silver and without silver did not have any negative effect on the functional activity of Vero cells. As a result of the research, hydrogel polymer nanocomposite materials based on polyvinyl alcohol, polyethylene glycol, and silver nanoparticles were formed. As an alternative to electron beam reduction, ascorbic acid was utilized to reduce silver ion to nanoparticles, allowing for hydrogel cross-linking at a lower dose. Using the method of wide-angle X-ray scattering, it was established that hydrogel materials based on PVA pack form a semi-crystalline structure, and the presence of metallic silver in the studied samples was confirmed. It was established that polymeric hydrogel materials with silver exhibit antimicrobial activity against Staphylococcus aureus and Escherichia coli and relative antiviral activity against influenza A virus and herpes simplex virus. It was established that the studied polymer hydrogel materials with silver nanoparticles do not show a toxic effect on MDCK and Vero cells. I want to mention again that this work was carried out in the frame of the project from National Research Foundation of Ukraine. And thank you, dear colleagues, for your attention.
Thank you, Ilya. Do we have questions in the conference hall? No? Probably in Kiev from internet. So what I have to say, being a student, Ilya is one of the main executors of our national fund project, and for example, I don't have any questions to him. Those we used while I was with a broken leg. We used our materials to aid it also, so it works, and that is confirmed by me, let's say, and by our surgeries. Okay, probably any questions? Okay, so Ilya, thank you very much.
Thank you very much for inviting me, letting me to present.
So dear colleagues, our section is finished, and please enjoy your coffee. We meet in 15 minutes here for the last section. Рома, ты здесь? Вы хочешь перенести? Ну, 416. Серый, я же 12, да, по-моему? А, подожди, проверь. Ну, прости, идея, мне надо сказать. Ну, прости, идея. А можешь ли вот вас кандидата по да. Я с мессенджера открыт, а как можно отправить файлы некрасивые с хренами? Не рабочий. Я не знаю, машина. Можешь включить? Она уже там, но так это я особенно, она будет, это, не знаю,
Угу. Ага, так. Не, выключен, да. Тут три положения на среднее, да? Ага. Оно просто с задержкой, да? Да. А, ну все, тогда сейчас. Какие? А ну сейчас. Сейчас. А это же мы аппроксимации делали из этих параметров. Ну, мы же в каждую неделю ходим вот так вот. И все. Да, 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 да. Что-то пересчитать нельзя просили. Ну да. Ну, короче, да, да, слава Богу. Ну да, 12. Получается, после брейка 12. Да, да. Да, ну салатчик постоянно будут такие. Это аккуратно, чтобы... Начинает просто как человек. Первый суперсвет, и жди, я пробовала. Да, да. Я не смею поверить. Прикольно разговаривать, тренажерный зал тоже включен в стоимость номера? Да, 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 шикарно, конечно. Нет, это шикарно. Да, да. Ну, я не видел, это начинает. Я думаю, что там а вот этот новый Виктор. Все правильно.
Ну, что, посмотрите. А здесь тоже презентация, да, отображается?
Ну, вот здесь,
И
да.
то же самое, что на
То и
экране.
там, да.
А
И
как эту штуку управлять?
смотрите, тут две стрелочки есть.
Вперед назад.
Только да, тыкать надо
А,
туда,
вот там, да?
вот там пультик находится. Видите, и оно меняется.
Я понял. Можно? Я понял.
Да, 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 конечно. Вот это, да,
Мгм.
все, и перескочил. Это
Всё,
назад.
спасибо.
Да не за что.
Спасибо.
Да.
Yesterday we talked about период полураспада. Now is next level. Most people are very close to this room. But anyway, we are starting our final plenary presentation, final plenary session. We will have 3 good presentations. Let me introduce the first speaker, Ruslan Gubatyuk, with his researches about mathematical modeling of heat and mass transfer processes of electron beam melting of ingots for high strength titanium alloys. So, welcome. We are listening to you.
Hello, everyone. Title of my presentation, the mathematical modeling of heat and mass transfer process of electron beam melting of ingots of high strength titanium alloys. Don't worry. Oh. Electron beam cold-Haas melting is effective method widely used in industry to produce defect-free ingots of titanium and its alloys. The principle of electron beam melting process is horizontal feeding of a feedstock position 4 at a given speed into the melting zone is melting by electron beam from GANs position 2 and 3 over of cold-Haas position 5. As the cold-Haas is filled, the liquid metal is poured into the crystallizer position 6, whereas ingot position 7 is the required length is formed.
Let me switch for you.
Next slide, please. Mhm. One of the key processes during electron beam melting of titanium alloy ingots is metal crystallization. The transition of metal from a liquid to a solid state is accompanied by complex heat and mass transfer process and high-speed physical and chemical process. The irregularity of temperature in ingot the metal volume affects the formation of the crystallization front profile and leads to difference in the structure and the chemical composition of the metal in the center and periphery of the ingot, also in the presence of shrinkage and liquefaction phenomenon. In this regard, the scientific task arises to create mathematical model to heat and mass transfer process during the formation of a titanium alloy ingot. Next slide, please. Numerical simulation were performed for process of crystallization of an ingot titanium alloy TA15. Format is a 150 millimeters diameter in flow through crystallizer. The ingot drawing speed was 18.7 millimeters per minute, which corresponds to continuously casting of an ingot with a productivity of 4 kilograms per hour. The metal temperature at the inlet to crystallizer was 2061 Kelvin and jet cross-section was 10 by 10 millimeter. The power of electron beam of the liquid pool distribute in the peripheral zone and amounted to 21 kilowatts. Next slide. To simulate the process, a mathematical model was formulated which includes the law on conservation of energy, momentum, and mass. The Darcy force was introduced into the equation of motion, which is necessary for the possibility of speed separation in the mushy and solid zones. The calculation hydrodynamic process that occur during the continuously casting of titanium alloy into the crystallizer was based on the following assumption. Liquid metal is poured into the crystallizer continuously at some speed. At constant ingot extraction speed is ensured. The mirror of the melt pool is a flat surface. The melt was considered a viscous, incompressible liquid. The movement was assumed to be laminar. Next slide. The fast-fail method was used for numerical simulation. The liquid phase, the transition to phase zone, as well as the solid phase of the ingot are modeled is one subregion. The interface boundary of the liquid-solid alloy is viscous transition zone, is which the boundary is determined by the temperature of the liquidus and solidus. The metal parameters change according to proposed law relative to the volume fraction on these phases. The volume fraction of the metal of the transition zone from temperature is the smoothest function based on the mathematical erg function. To take into account the head of the phase transition during solidification of ingot and the alpha-beta transition and the apparent head capacity method was used. Next slide. On slide 7, the calculation area from the study of the specified process is presented. The boundary of the calculation area G1, G7 are illustrated. Boundary condition for the presented calculation area are given in a table. The distribution of the thermal power of electron beam on the surface of pool mirror varies according to the Gaussian law. The dependence of losses from the surface of the liquid melt due to evaporation to take in accordance with depending on the temperature. Next slide. Slide 8 presents approximate dependence to thermophysical parameters of titanium alloy. When modeling, they were accepted with a smooth transition in stepwise jump of values. Next slide. As a result of the calculation, a graph of the temperature distribution on the surface of the liquid metal pool is presented. It was established that the power of the electron beam and geometric position on the surface on the bus significantly affect on the crystallization front and the temperature distribution in the ingot. The position of crystallization front on the slide is shown by two isotherms with temperature of the liquidus and solidus. The value of the temperature range of the transition during the calculation was assumed equal to 50 kelvins. Next slide. Slide 10 shows the calculation three-dimensional distribution of the temperature field and direction of the velocity vectors of the metal flow in the crystallizer with reduction of the ingot pulling speed to the bottom. Stream of liquid metal spread from a place of its pouring into the walls of the crystallizer, forming a small vortex. From top view, a diametrical distribution of metal flow is observed, which is caused by the action of flow from liquid metal pouring into the crystallizer and the thermal power from the electron beam. The result calculation of melt movement trajectories showed an adequate effect of the Darcy function on inhibit the movement of metal in the solid phase. Next slide. On slide 11, a macro slice of the ingot is presented. A compression of the calculated crystallization front and the crystallization front of the ingot itself, indicated by dashed line, indicates a good match between the profile of the front and result of mathematical modeling. The macro slice is characterized by absent of shell and discontinuous of the ingot macrostructure has crystal close acucate, which is indication of a good ingot quality. Excuse me. Next slide. The slide presents the main conclusion of the work carried out. Based on the results of mathematical modeling, the temperature field and the laminar hydrodynamics flow of the molten metal in Ta50 titanium alloy ingot, which a diameter of 150 millimeters were obtained. The geometric of the liquidus solidus two-phase zone was determined, which determines with the crystallization front of the metal, the position and geometric, which significantly affect the quality of the ingot formation. It was found that the distribution of the power of the electron beam on the surface of the pool has a very significant effect of the heat and mass transfer at a constant rate pouring molten metal into the crystallizer. Which an electron beam heating power of 21 kilowatts and an electron beam position of 60 millimeters from ingot axis and melting speed of 40 kilograms per hour, such as crystallization froth is formed that ensures good quality ingots. That's all. Thank you for attention.
Thank you, Ruslan. Welcome questions.
Ruslan, thank you very much for good presentation. And I have a question. Is it possible to simulate melting of another form of ingots?
Could you repeat, please, your questions?
Yes, okay.
Yes.
Okay. Thank you very much.
Thank you for your presentation. And as I understand, you solve three-dimensional problem, and it is very time-consuming problem. And how much time does it take to carry out simulation? And what computational resources do you use for this?
For numerical simulation, we used the server Hewlett Packard Proliant 9th generation. Time of calculation time was 6 hours. One calculation, да. Yes.
I have a question. Can you show, please, the velocity distribution in the God? This one, the left. I see the arrows which aims from the surface. Does it mean that the liquid metal tries to jump from the melting pool, or what does it mean?
Ну, я зрозумів.
Origin of the arrow is inside the WRT. So on the boundary, the normal component is No, it is just a problem for visualization.
Ну, да, это just a visualization.
It's inside the WRT, but there is no arrow. This origin on the preset on the so the velocity is there.
Which software you simulated your model, and is this new results, or it's already or you already published it?
Thank you for the question. It's new results, not published. The software we used console multiphysics. No, yes.
In your presentation, you show the results for high strength titanium alloys. Titanium alloy. What do you think about another classes of titanium alloy?
Ну, результати схожі будуть. Similar results.
I see very interesting presentation, a lot of questions, and our room is full again, like it was on Thursday. I also have a question. You have used some input data. Maybe they are unique for the material. And where did you get the physical properties what you use for calculation?
In our institute, there is a department that can get the physical properties different alloy. We use the data that they provide us.
Thank you again. I don't have a question here. I think so. So let's right. Let's move to our next presentation. will be online. Valery Primitka with type of changes in the structure and properties of high chromium cast iron, soldered with carbide encapsulation in a charge of powder wire. So, welcome, next presenter.
Good afternoon, dear participants and guests of conference. Do you hear and see us well?
Greetings, glad to see you.
Do you hear us?
We don't see presentation, but see you.
Presentation. Okay. Do you see presentation? Please tell us.
Yes, yes, we see.
Thank you. Thank you. First of all, I want to introduce myself. My name is Igor Kolomoets. I'm Associated Professor and Philosophy Doctor of Dniprovsky State Technical University, and I will represent the group of authors during the report. So if you hear and see us well, we thank you for invitation to this conference, and thank you for participation. We want to present results of research on the topic that sounds like changes in structure and properties of high chromium cast iron soldered with carbide encapsulation in a charge of powdered wire. The relevance of researchers lies in service life of machines and mechanisms for the extraction of minerals, as well as those used in metallurgy and construction, is significantly limited due to intensive wear and tear. To increase the resource of mentioned objects, materials with increased resistance to the corresponding types of wear are used in their manufacture. At the same time, the surface strengthening on working surfaces of the restoration is carried out by chemical and thermal treatment, spraying, and electric arc surfacing. Here we see the process of preparation of powder wire charge. This is the scheme of process, and this is the complete mixture. For uniform distribution and removal of moisture, drying was carried out in an electric oven at 220 degrees of Celsius for 15 minutes, followed by sieving through a 400 micron sieve. Chromium carbide plastic was added to the wire charge in the mixer. Plastic spraying was carried out from a distance of 2 or 250 millimeters on particles, excuse me, with a size of 0.3 or 0.4. After drying, the particles were shaken and the process repeated to cover the entire surface. Then the material was dried in an electric oven at 112 degrees of Celsius for 12 hours, followed by sieving through a 400 micron sieve. Here we see equipment and modes of hard facing, and also the appearance of hard face samples for test of microstructure and chemical composition, and for test of wear resistance. Hard facing was executed on device crystal PNP 2.5. Metallographic studies included a spectral analysis of the chemical composition of the deposited metal. It was performed on spectrometer Spectrum Max, and metallographic studies were obtained with electron microscopy. Wear tests were performed on Mi-1M friction machine with a force of 1.5 kilonewtons according to the roller scheme. Chemical composition, here we see chemical composition of hard face samples. In the case of encapsulation of chromium carbide particles, sample 2 and 3, an increase of presence of carbon in heated metal is recorded. Moreover, the use of polyurethane unicast caused a more significant jump in carbon values, and use of fluoroplastic caused a significant increase of chromium values. Here we see the microstructure of deposited metal. The microstructure of metal with standard flux wire Veltec N630 has a little grid matrix in which excess carbides are fixed in the form of lamellar discharges. Moreover, in the fusion zone, the size of carbide deposits are smaller. In the case of use in surfacing powder-coated wire, coated with chromium carbide particles and unicast polyurethane, the metal acquires a structure of super-eutectic cast iron. With the additional modification of powdered fluoroplastic to the charge, a significant grinding of carbide discharges are also recorded. Even with sequential application of 3 layers by arc surfacing, the dispersity of structural components is preserved. Here we see results of wear test. Unlike the use of standard wire, the original leads to gradual increase in hardness over the time during 1.5 kilonewton loads. This is caused by strain hardening due to load intensification. Here we see change of hardness and mass loss during 12 hours of research. When testing sample number 1 with the metal hard face with the standard wire at the running stage, there was a decrease of hardness and decrease of mass loss. The addition of plastic to the charge caused a decrease of initial hardness. Here we see of the metal and it was 5.3% compared to the case of using the standard wire. Sample number 2 is characterized by deformation hardening during the entire period of actual wear, which is confirmed by parallel increase in hardness and mass loss. Here we see it. Comparison of change in mass loss during 6 hours of actual wear. Here we can see in comparison with a case of 1 kilonewton, the predicted intensification of the destruction observed due to the increase in the load of the contact surface, which is confirmed by increase in mass loss by an average of 7 times. Under conditions of increased loss, a significant role played by deformation hardening of the samples, and as a result, their embrittlement. And as a conclusions, we can say that the effectiveness of the scheme for regulating the composition, structure, and properties of the deposited metal due to the preliminary coating of the flux wire charged with plastic was experimentally confirmed. It has been established that the use of plastic during the formation of the charge of the hard facing contributes to the grinding of structural components, primarily carbides, ensures the saturation and the heated metal with carbon and the formation of structure favorable for wear resistance. The addition of plastic to the charge also caused a decrease in the initial hardness of the metal applied by 5.3% compared to the case of using a standard wire. A metal-to-metal wear test recorded that recorded a 1.5-fold reduction of mass loss of the samples hard-faced with the test wire in 12 hours of rolling friction under a load of 1 kilonewton. The report is finished. Thank you for attention, and thank you for invitation.
Thank you very much.
Thank you.
Thank you very much for your presentation. Any questions to the speaker? Okay.
Thank you for your presentation. In the conclusion number 2, you state that the heated metal, saturation of the heated metal with carbon. I have a simple question. Why can you use the metal with enough carbon at the beginning? Why you need the plastic to add the carbon? And why you cannot take a steel with enough percentage of the carbon?
We use plastic for increasing the term of existing of weld bed для існування зварювальної бани. Ну, чому ми використовували пластик?
А пластик для збереження від значного випаровування компонентів шахти.
And also plastic was used for good saving of components of the charge of hard facing wire.
І регулювання часу взаємодії.
And regulation of time of
взаємодії компонентів з рідким розпалом.
Of participation of components of wire with liquid metal. That was the purpose.
Thank you for answering.
Thank you.
Thank you. More questions from Kiev, maybe? Oh, thank you again for starting the presentation. And the next presentation will be
So next presentation.
person.
Thank you.
Thank you.
Bye.
Thank you. But before present the next speaker, I will ask to Kiev and to all other who join us in Zoom to return to the our session. We will get an extra presentation, a speaker from Germany Welding Society. Hope it will be interesting. So if you have a schedule, please change it a little. So now the next presentation, the last of this section, Alexander Babachenko with topic development of chemical composition and heat treatment of perlite steel for high strength railways rail. So welcome.
Я зрозумів. Якщо не буде працювати, піддалі інструмент. Що? Я зараз скажу пару слов. Так, скажіть, будь ласка, щоб не я.
This presentation will be unique. It will be in Ukrainian. Oh.
Yes. Добре. Шановні учасники конференції, я представляю, перше це я прошу вибачення, моя доповідь буде на українській мові, але так. Я представляю Інститут чорної металургії Національної академії наук України, місто Дніпро, і тому перед тим, як я перейду безпосередньо до своєї наукової доповіді, я хотів би декілька слів сказати про наш інститут. Наш інститут на сьогодні проводить фундаментальні та прикладні дослідження по всім напрямкам чорної металургії. Я маю на увазі доменне виробництво, в тому числі і позапічна обробка човну, сталеплавильне виробництво, в тому числі позапічна обробка сталі, обробка металів тисків, а також термічна та термомеханічна обробка різних видів металопрокатів, зокрема залізничні колеса, осі, фасонні профіля прокату, арматура, катанка та інші. Наш інститут вже багато років успішно співпрацює з майже всіма українськими металургійними підприємствами. Тепер безпосередньо до доповіді. Доповідь називається «Розробка хімічного складу та режимів термічного оброблення перелітних сталей для високоміцних залізничних рейок». На сьогодні, до війни в Україні залізничні рейки виготовлялись відповідно до українського стандарту ДСТУ 43-44. На цьому слайді представлені механічні характеристики, представлені вимоги по механічним властивостям до сталей по ДСТУ. Намувались наступні характеристики: границя міцності, границя плинності, відносне подовження, відносне звуження, ударна в'язкість, а також твердість. Але по існуючій технології проблемно було виготовляти залізничні рейки підвищення надійності, підвищення довговічності, зокрема по європейському стандарту ЄН 15674. На цьому слайді також представлені вимоги до рейок за цим стандартом. Основною проблемою при виготовленні таких рейок це було досягнення рівня твердості на глибині. Це було досягнення рівня твердості на глибині 20 мм. При цьому цей рівень повинен бути не менше 370 HB. Наша технологія, українська технологія і український стандарт ДСТУ нормує вимоги по твердості лише на глибині 11 мм, причому це значення повинно дорівнювати 321 HB. Тому завдання розробки технологічних параметрів вироблення залізничних рейок підвищення довговічності, з моєї точки зору, на сьогодні для України є дуже актуальний. Дослідження, які були проведені в Інституті чорної металургії, показали, що одним із перспективних напрямків у розвитку цього питання є розробка нового або вдосконалення існуючого хімічного складу сталей, який би забезпечив підвищення прогартованості, при цьому з формуванням перелітної структури за перерізом головки рейки, і відсутність структур закалки, я маю на увазі мартенситу, і відсутність виділення структурно-вільного цементиту по границям зерен. Для вирішення цього питання в інституті були виконані наступні дослідження. Були виплавлені дослідні сталі різних хімічних складів. Лабораторні, це були лабораторні виплавки. От на цьому слайді схематично показана ця процедура виплавки сталей. Внизу в таблиці показані два основних хімічних склади, які нас зацікавили. Це сталь, ми умовно назвали 1 і умовно 2. Перша строчка в цієї таблиці – це та класична сталь К76Р, яка на сьогодні використовується в Україні для виробництва залізничних рейок. У порівнянні з цією сталі, наші сталі, тут ми збільшили вміст вуглецю до 0,84, а в наступній до 0,9, тобто це вже загартектоїдна сталь. що з точки зору наших фахівців є перспективне, а також мікролегування бором 0,3 і розкислення кальцію. Після виплавки була проведена, тут показана порізка цих проб. Після виплавки була проведена гаряча пластична деформація наших проб, і за допомогою математичного моделювання була побудована термокінетична діаграма нашої дослідної сталі з метою вибору інтервалу швидкостей охолодження, які могли би забезпечити формування високодисперсної перлітної структури. От, наприклад, такої, як показано на цьому слайді, де рівень твердості дорівнює 368 АВ. Потім була проведена термічна обробка наших дослідних проб. Термічна обробка заключалася в наступному. Нагрів до температури 900 градусів, потім витримка при цій температурі протягом 50 хвилин і наступне прискорене охолодження з різними швидкостями. Оці різні швидкості охолодження були розраховані, як я вже сказав, на основі розрахункової термокінетичної діаграми. І це були наступні швидкості охолодження. 0,52 градуса Цельсія в секунду, це синій колір. 2,3 фіолетовий і 5,1 це сірий колір. Експериментальні результати показали, що в цьому інтервалі швидкостей охолодження формується перелітна структура різного ступеня дисперсності. От така мікроструктура показана на слайді, і ми маємо наступне. При швидкостях 0,52, 2,3 і 5,1 ми маємо міжпластинчну відстань переліті, яка дорівнює 0,17, 0,11 і 0,10 мікрона. Також було встановлено, що в вказаному інтервалі швидкостей охолодження практично відсутні структури гарту. Ми маємо перелітну структуру і десь близько 2% виніту. Результати досліджень показали, що в інтервалі швидкостей від 5,1 до 3,2 ми маємо рівень твердості від 398 до 415 HB, що відповідає вимогам європейського стандарту. Тобто ми при таких швидкостях охолодження, при такому хімічному складі, ми можемо досягти необхідного рівня твердості в наших залізничних рейках. Також в роботі були проведені дослідження впливу швидкості охолодження на міжпластинчасту відстань і на твердість. І отримані залежності від швидкості охолодження. От червона – це у нас залежність твердості від швидкості охолодження, і сіра – це у нас залежність міжпластинчатої відстані, також від швидкості охолодження. І також були встановлені закономірності впливу міжпластинчатої відстані на твердість нашої перелітної сталі. Після прискореного охолодження було проведено отпуск дослідної сталі, який заключався в нагріві до 200 градусів і витримки 1 час. І механічні властивості наших дослідних сталей, я маю на увазі 1 і 2, представлені на цій таблиці на слайді. І в якості основної для наступних досліджень була вибрана сталь з умовним маркуванням 2. І в цій сталі, як ви бачите, можливо досягнення рівня твердості 370 HB. Ми досягли 368, тобто це майже той результат, який нам потрібний. І коротко висновки по цій роботі. По-перше, в роботі були встановлені закономірності фазових перетворень сталі 0,9% вуглецю, 0,89 марганцю, 0,39 кремнію, 3 десятитисячних бору і 6 десятитисячних кальція. При безперервному охолодженні було встановлено, що при швидкостях охолодження до 5 градусів Цельсія в секунду у нас формується перлітна структура різного ступеня дисперсності. При подальшому охолодженні від 5,1 до 12,8 градусів Цельсія в секунду ми маємо структуру перліту і мартенситу. І при подальшому охолодженні вище 12,8 градусів Цельсія структура повністю складається із мартенситу. В роботі були встановлені закономірності зміни твердості і міжпластинчатої відстані нашої дослідної сталі при швидкостях охолодження до 5 градусів Цельсія в залежності від швидкості охолодження. І останній висновок – то, що наша дослідна сталь з от таким хімічним складом, який представлений на слайді, була рекомендована для дослідного промислового опробування. Дякую за увагу.
Thank you. What questions do you have?
Питання. Можна питання?
Да.
Ярослав Іванович, Олександр Іванович, добрий день, Лобанов.
Добрий день, Ігор Михайлович, рад вас чути.
Олександр Іванович, є питання. Які перспективи промислового виробництва представлених вами реєк із перлітної сталі?
Ігор Михайлович, дякую за запитання. Ну, по-перше, я вам відповім на першу частину про перспективи виробництва реєк взагалі в Україні. На сьогодні виробництва реєк в Україні, на жаль, немає. І це...
Я тому і задав вопрос. Питання. Тому і задав питання.
Да. Значить,
Тобто немає перспективи, так?
Але наскільки мені відомо, тому що я приймав участь у цих переговорах, Мітінвест зараз зацікавлений питанням налагодження виробництва залізничних реєк на своїх підприємствах. Це питання, як вони нам сказали, зараз вивчається.
Дякую.
Next question.
Питання є. Туди.
Дякую за цікаву доповідь. Скажіть, будь ласка, ви використовували два види сталі, які виплавляли. Це були повнопрофільні зразки реєк, чи це були якісь менші зразки?
Ні, зразки це були ті, які відповідали по геометрії стандарту. Тобто, якщо це удар, це було 10 на 10, я так умовно говорю. Якщо це на розтяг, то це були п'ятикратні діаметри, я не пам'ятаю, але це були стандартні зразки для механічних випробувань. У нас дослідні були плавки, тобто це була не промислова плавка, а це була такий дослідний зливок десь масою до 20-25 може кілограмів.
Можливо, я просто трошки некоректно задав питання, перефразую трохи. Першочергово ви виплавили рейковий профіль чи ні? І термообробляли його?
Термообробляли. Спочатку гаряча пластична деформація, а потім термообробка.
Так, але це був повнопрофільний профіль рейки, профіль, наприклад, 65, який використовується в Україні, або у вік 60, або це були зразки.
Це були звичайні зразки. Вся ця робота побудована на лабораторних дослідженнях. Завдання було розробити такий хімічний склад, який би забезпечив формування при перелітній структурі, я підкреслюю, в рейках повинна бути тільки перелітна структура, матинці, тобто структура закалу випускається. При перелітній структурі забезпечив рівень твердості не нижче 370 HB. Це було головне завдання. Звичайно, це були не рейки.
Дякую.
Можна? Дякую за цікаву доповідь. В мене питання такого характеру. Ви навели дуже прецизійні склади сталий. Будь ласка, можете прокоментувати, який розкид по вмісту хімічних елементів є припустимим? Розкид по вмісту хімічних елементів є припустимим. Розкид, так. Ну, отримати точно такий хімічний склад.
Ну, ви знаєте, у нас, я привів тільки 2 плавки, у нас їх було десь 8, по-моєму. Тобто завдання не ставилось розробити технології виплавки сталі. Тому тут немає ні інтервалів зміни, нічого. Завдання ставилось, визначити можливість досягнення отого рівня твердості для таких. Розумієте, в чому проблема? Ми беремо хімію і просто фізично чи матеріалознавчо цей хімсостав він не може забезпечити при перелітній структурі отакий рівень твердості. Ну і таке було за ним. І тому на цій таблиці ніякі, так сказати, варіації елементів не представлені.
Добре, дякую.
Ви порівнювали 2 зразки, зразок 1 і зразок 2, але вони відрізнялися просто за кількома параметрами. Там в зразку 2 було більший вміст вуглецю, а також були оті мікродоби, як їх правильно назвати, з маленькою концентрацією, мікролегування. То все ж таки за рахунок чого зразок 2 кращий? За рахунок вмісту вуглецю чи ось того легування?
За рахунок чого нам вдалося досягти рівня твердості? Так, зараз я можу повернути. І ще назад. І ще назад, будь ласка. Оце. Значить, по-перше, підвищили вміст вуглецю. Незначно, але підвищили. Але основне те, що ми додавали бор, він, властивості бора, він підвищує прогартованість. Хоча тут це не класична прогартованість, це не мартисіта. Тобто нам вдалося на більшу глибину отримати більш дисперсний переліт. А кальцій, це було встановлено експериментально, тому що якщо ми плавали без кальція, це як розкислювач для глибокого розкислення. Коли ми плавали без кальція, зокрема, оця сталь, там була дуже погана макроструктура. Були пори, були різні дефекти. Тому на сьогодні на цьому ми зупинилися.
Азот впливає. Азот.
Азот, то остаточний. Вибачте, то залишковий. Привели, як привели.
У вас сталь номер 2 заефектоїдна. І при такому хімічному складі повинна бути сітка карбідів по границям літніх колоній. Як вам вдалося запобігти цьому?
Дякую за запитання. Це дуже значна проблема для заефектоїдних сталів, тому що якщо буде сітка карбідна, то це властивості, це за рахунок вибору оптимальних швидкостей охолодження, щоб ця сітка ще не встигла сформуватися. Тобто тут у нас карбідної сітки ми не наблюдали експериментально.
Дякую. More question? Все? Тепер ми знаємо, що треба робити, щоб було багато питань. Well, let's send. Давайте ще раз подякуємо вам.
Дякую.
This session is closing. Plenary after session will be start in 1 hour at 13. Also will be an extra invitation and closing ceremony. So stay tuned on.